Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at how we use integration to find work done by a variable force. When you're finding work done by a constant force, work is defined as the product of that force times distance. But when you have a variable force or continuous force, we need to use integrals to find the amount of work done. So the definition is the work done by a continuous force directed along the x-axis from x equals a to x equals b is work is equal to the integral from a to b of f of x dx. The example that we're going to take a look at in this video is the work done in stretching a spring. The amount of force in stretching a spring is variable. It changes depending on how much you're stretching it and from what position to what position. So let's take a look at what our f of x is going to be when we're looking at work done in stretching a spring, and we'll take a look at a couple of examples. So the function that we're going to use is f of x equals kx. And this function is called Hooke's law. And it's a direct proportion. Hooke's law states that the amount of force required to stretch a spring is directly proportional to the amount it is stretched. So you'll need a set of values that will allow you to find k. Once you find k, then you have your integral for finding work. But you have to be very careful what you use for a and b in this integral. A is the initial distance that the spring is stretched from the normal length. B is the final distance that the spring is stretched from the normal length. So let's take a look at a couple of examples so I can illustrate what I mean by this. In our first example, it tells us a spring is stretched 10 centimeters by a force of 3 newtons. It asks how much work is needed to stretch the spring 40 centimeters. If the question just asked us how much force is required to stretch it, we would just set it up as a direct proportion and we wouldn't need integrals at all. But this is asking the amount of work. So our function for amount of work will be the integral from a to b of kx dx. We need to find k. So remember, f of x is equal to kx as our equation for a direct proportion. F of x represents the amount of force, and x represents the amount it's stretched. So the amount of force is 3 newtons. The amount is stretched is 10 centimeters. I like to work with my length in the base unit of meters, so I'm going to divide by 100 to get 0.1 meters. So that will be my x, and then when I find my constant, I divide by 0.1, I'm going to get 30. And what that represents is the amount of newtons per meters required. Now that I have k, I can put that into my formula. 30x dx. We need to find a and b. So a represents the initial distance from the normal length. We don't even know what the normal length of the spring is, but we don't need to know it. We just know that it's starting at 0 meters. We haven't stretched it yet, so it's 0 meters from the original length. And B, we're stretching it 40 centimeters from the original length. So B is 40 centimeters, which is 0.4 meters. So we plug those values in, and now we integrate. When we put 0.4 in, square it, times it by 15, we get a value of 2.4. And the unit of work is force times distance. So our force is measured in newtons. Our distance is measured in meters, so it's newtons times meters, also called Newton meters. And another unit that's used to represent work is joules. The symbol for joules is a capital J. it's equivalent to a Newton meter. So you could write it as 2.4 Newton meters or 2.4 joules. Let's try another example. This example is a little different than the last one because it does give us the natural length of our spring, 8 centimeters, and then it tells us a force of 12 newtons stretches it from 8 centimeters to a length of 10 centimeters. So I'm going to use that piece of information to find my K. Remember, f of x is equal to kx, that's direct proportion, Hooke's law. So a force of 12 newtons will stretch it a length of, from 8 centimeters to 10 centimeters is 2 centimeters. I'm going to change that to meters. So x, the amount it stretched, is 0.02. I divide 12 by 0.02 and I get a constant of proportionality of 600, and that would be newtons per meter. I put that value in for K. And then the other thing I have to determine is the A and the B. So A is the initial distance from the original length. So I want to know how much work is done in stretching this spring from 10 centimeters. So 10 centimeters is 2 centimeters more than the original length. So my initial distance from the original length will be 2 centimeters, which is 0.02 meters. And B will be the final distance from the original length. So if I'm stretching it to a length of 14 centimeters, 14 minus 8 will be 6 centimeters, which is 0.06 meters. So you have to be very careful in finding A and B. Remember, it's the initial and the final distance from the normal length. So we're going to put 0.02 in for A, put 0.06 in for B, and now we're going to integrate. So that will be 300 x squared when I put 0.06 in my function and 0.02 in my function and subtract, I get a value of 0.96. It's work. I know my unit for work is newtons times meters because I was working with my force in newtons and I was working with my distances in meters. So that would be the amount of work done. Hopefully by now you've seen that integration is very powerful. We've used it to do a number of things. Calculate area under curves, area between curves, volumes, centroids, moments of inertia, velocity, displacement, work done by a variable force. I'm now going to turn my attention to techniques of integration or methods of integration. So far we've been integrating the same kind of function over and over and over again, but there are many more functions that you will be required to integrate. So when you're ready to start that journey, I'll see you on the next video.